Now we enter the other room. Can you try to share something? Then that's the second. You can try to proceed as the second speaker and check. Sound. Sound not working.
Yes, the sound is go there because it's the camera of the presentation. Okay, and the sound goes there.
But we don't want it. No sound here.
Okay.
Microphone and that.
Yeah.
Can we try this?
This?
Oh, that's it. It's already in.
Okay, but it's muted and
You can say something.
yeah,
Can
it's
you ask the
muted and don't. Não conseguem ouvir. Okay. 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 Here.
Hello. Are you ready? Ready? Can? Naka-open na yung yung slide mo. Naka-open. First slide. Naka-unmute. I-unmute yung yung okay.
Hello, good day, everyone. Can you hear me? Hello.
Yes.
All right.
There. Okay.
Okay. You want to see that?
Yeah,
Yeah.
Should I begin? Sorry, I didn't get it. Should I begin?
Maybe you
can you share the slide?
Okay, sharing the slides.
Okay, good, okay, good, good. But I cannot see the continue? No?
Yes.
Yeah, let me switch my camera to.
Okay, good, good.
You can see that.
Okay,
should maybe maximize
maximize this one.
Screen. Screen is full.
That's the maximum?
Yes.
Okay. Okay, can you hear me?
Yeah,
Earth?
yes, sir.
Can you?
Yes, sir. Yes, sir.
Okay, you might have missed my announcement, something like the presentation is good for each slot at 20 minutes, and then you have 15 minutes presentation, and then 5 minutes question and answer. Is that okay with you?
Yeah, yes, sir.
Okay,
Yes, sir.
so shall we start? Go ahead once you're ready, please.
All right. Thank you, everyone. Thank you for having today. Thank you for um, coming here for this presentation, and I'm very excited to present our study on two-stage pavement distress detection and classification using UAV imagery in unstructured road environments. Again, I am Earl Alleluia. I am from Mindanao State University, Iligan Institute of Technology, Philippines. And on behalf of my co-authors, I'm going to present to you our study. But before I begin, I would like to ask this interesting question. Do you enjoy road trips? Like personally, in my case, I love to travel. And as a young researcher, I want to go to other places to travel and to enjoy life, to enjoy the food, something like that. But road trips is one of the bucket list. Like a 3D road trips would be a for me is it is a fun thing to do. But unfortunately, the setup of road trips for um, advanced countries like for probably countries in Europe or Japan or China or America is different to what we have in the Philippines. For example, I would like to highlight here the difference between the structure of the road itself. So advanced countries like Japan in this photo in the left photo, you can see that the roads are structured. There are clear road markings, safe boundary rail, smooth road, and structured road design. And fortunately, the Philippines is quite behind because you can see in the photo at the right, um, a man crossing the street without a pedestrian. The road is rough, and even road markings are not clear. And this is becoming a challenge in the Philippines. So, how to address this? So, when we go to the government agency, which is the Department of Public Highways, the DPWH in the Philippines, we found out that they are following this four process cycle, the PMS, the Pavement Management System. It started with, of course, the this is the R&D part, the pavement design and testing. But more importantly, DPWH, they are working more closely on the construction. And of course, in order to have a better PMS, there should be an evaluation process wherein the road is being inspected. And once results are out, then that's the time that they have to come up with a financial plan and how to restore or maintain the pavement or the road itself. But unfortunately, this cycle here is not. efficiently followed in the Philippines. In fact, we have poor PMS, which results on this photo right here. You can see an excavator trying to dig some holes. Then that's only in the Philippines that you would ruin the perfectly fine road. So what happened here is that we have this asphalt in the photo, but then again, an excavator is trying to dig out the asphalt, even though the better is at its perfectly fine status. Now, when we check and investigate what happened, major problem is that there's an overlapping timeline between these processes. And in fact, what happens is in the evaluation process, it mostly takes time in with the manual inspection method. And you can see in the photo that some um, workers here are having the roller, the some instruments and apparatus to measure the cracks or the distresses in the road. Now, the evaluation in the Philippines, for example, takes a lot of time. And in fact, what I would say an average of 6 months evaluation, because they have to come up with a plan, like when to investigate, when to inspect, and then in that 6 months, the restoration will be a problem because by the time it happens, the road is already destroyed or at its inefficient status. Now, the problem here with the poor PMS results because of the overlapping timeline. Now, to address that, um, we check with the existing literature, and in some countries they have presented several techniques. Like we found many references that are using e-car augmented with some sensors. That's a good solution. However, it's very costly. And on some papers that we read, they are using aerial inspection using UAV. And in here, you can see on the there are three papers that I cited, and in fact, the results are very decent. Like it's above, and the first photo it's above 86% or around 80%. In the second photo, they can determine the crack classifications, even detecting potholes, repairs, delimitation. And these are excellent papers. Now, we can do this, but the problem in the Philippines is that after having these results, what's next? The, but basically, the basic or the practical question right now for the Philippines is how do we interpret these detection results for the pavement management system? So what we did in our research project, we really contacted or have multiple meetings with the DPWH, and then out of this conversation, the key question is this: mainly, on how to they decide which part of the road should be prioritized based on this key question: how severe are the distresses in a 1 kilometer road distance? Usually, in their reports, they usually get um, their report is based on a 1 kilometer segment, and then they have this quantitative value out of that record to have a aggregate representation of the severity. And then yeah, we tried to address that by having the solution. For each pavement panel, we detect the distresses. So basically, at first, it's a binary classification whether the pavement is a non-distress or the pavement is a distress. And then in the distress hierarchy, there should be the classification of those distresses, like the sealed patch, the sealed crack, and the twin crack. And then we compute the severity based on this ratio, on this equation. Basically, what this means is that we count the number of severe or distressed panels out of all panels. So our steps is we obtain the data by data collection, dataset building, model training, and then model deployment. Then our results, we presented them to DPWH and then have their feedback on what to improve. So in our study, the paper that we 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 presented in this conference is basically out of this algorithm. So basically, we have a two-stage detection and classification, and then wait, I'm not sure if I'm anyway. There is two-stage classification, and then the first stage is more on parallel detection, and the next stage is more on classification. And then the results are based on answering how precise are the parallel decoders, which we found out that out of all the variants, the small variant for YOLO is better working on all of these tasks. Next one is we found out that what we propose, the refining algorithm, we found out that um, our our method on refining really improved the lane detection. As you can see here, that the orange part is more on the pavement panel detection, but our algorithm improved that based on the average false negatives and average F1 scores. Then finally, we come up with this overall result to represent our two-stage network, and we found out that based on precision and recall, our method was able to improve the precision. As you can see here, that using that typical panel detection and classification, the sealed crack and then the turn crack suffers. But the rest are, but on our two-stage architecture, it has been improved. And then to show you, I'm going to present a demo and allow me to check. Uh, all right. So hopefully you can see my demo video. And you can see here that there's an input image, and then the road lanes are detected, and the pavement panels are detected, and then some classes are four classes for the classification. And then these are some results on area 1, and then this one is for area 2, and then this one is for area 3. Yeah. And that ends my presentation, and I'm ready to have some questions if you have ones. Thank you. Thank you very much.
Okay, thank you. Okay, the floor is open for questions, comments. Okay, Rafael?
Just if you can ask him if it's used LiDAR or only visible imagery or LiDAR.
Again?
LiDAR or
LiDAR.
LiDAR. Okay.
LiDAR.
It, we explored using lidar on some of our research projects, but um, the uh, the the content of our paper, which we presented here, only uses RGB. But basically, what we have in the lab, we also explored RGBD, the depth, and also augmented that with lidar. More likely in different purpose. We use the RGB for detecting the cracks because visually they can be identified. But lidar, we use lidar for measuring uh, edge break, um, rutting, and I forgot the other things. But more likely more on deformation of the pavement panel, not more on basically deformations that has a 3D connotations on the pavement distress.
Okay, thank you.
Anything else? Okay, I have a quick question. Do you have something like a comparative study between this single stage and this two-stage approach of yours?
We have with um hopefully the screen is updated new part, but allow me to go to this part here. This compares basically the left part, the left figure shows you the baseline. It uses only YOLO as the baseline detector, and then vision transformer as the classifier. So in our study, since we incorporated road lane detection as well as the refiner method, we were able to improve the precision and recall. Basically, we addresses the false positives and the false negatives. But on
Okay.
regards to comprehensive ablation study, it was not presented in our paper here, but currently one of our student in the lab is working on the ablation study of our existing methods.
Okay. Anything else? Any more questions? Okay, not unless you have questions, then Earth, thank you very much for your nice presentation and hoping to see you next year.
Thank you so much. Thank you, everyone. Have a good day.
Okay, shall we proceed to the next speaker? It's online. It's,
Yeah, he's online, so all the rest will.
okay, did you
no,
miss, excuse me, you know the presentation is 15 minutes and 5 minutes for questions and answers. Are you aware of it? Hello?
hello. Can you
Ah,
hear me clearly?
yes, we can hear you, but I
Okay.
was just trying to emphasize that your presentation is 15 minutes, another 5 minutes for questions and answers. Is that okay?
Okay.
Okay, good. So once you're ready, please begin.
A second. Okay. Um, can you see my slides?
Yes, we can hear your slides, but I'm fine.
Okay. I'm starting. Good morning, everyone, and thank you, Chair. My name is Hubi Tai from St. Petersburg State University, and I'm presenting online today. This is the first of two companion papers in this volume, the technical one. It asks a simple question: what kind of ledger should a central bank digital currency actually run on? And we try to answer it with numbers using simulation. Let me start with why this matters. As of 2025, more than 130 jurisdictions are piloting a central bank digital currency. China's ECNY alone has passed 300 million users, and on
Can you change your slide? Not too much.
so you can't see my slides.
No. Peter, could you please first make full screen and then share that full screen?
Full screen.
Without your PowerPoint. And you did not change slides, so you didn't change slides.
Okay.
can you make full screen first and then share the
Can only see your face.
What about it? And now?
Can you try to make slides now?
Sorry, I can't hear you clearly. It's noisy.
Can you maybe hear better from here?
Yes.
Is it better from here? Like you did before? Yes, now we see full screen. Can you change the slide, make the second slide, third slide? So yes, now it works fine.
Oh.
Very good.
Okay. Sorry about
Please proceed.
that. Okay. Again.
I think we can let you start again.
Okay. Where are we? We try to answer it with numbers using a simulation. Let me start with why this matters. And as of 2025, more than 130 jurisdictions are piloting a central bank digital currency. China's eCNY alone has passed 300 million users, and on a centralized ledger, it clears over 100,000 transactions a second. So the question is no longer whether money goes digital, it's which ledger architecture carries it. Blockchain is the leading candidate because of decentralization, immutability, and programmability. But every architecture choice treats speed against control and cross-border reach. Those trade-offs are usually argued in words. What this paper does is attach numbers to them. The paper is built around four questions: how blockchain can serve as CBDC infrastructure, which capabilities are already proven in pilots, which bottlenecks are limited, and whether a tokenomic model can quantify the trade-offs. We make 5 contributions, but the one I will focus on today is the third, a 4-scenario simulation study, where implement a tokenomic model, calibrate it against published measurements, and validate it. Let me move through the survey quickly, then spend most of the time on the simulation. CBDC architectures sit on a spectrum. A centralized ledger eCNY, its example, gives instant settlement and very high throughput, but low transparency. A permissioned distributed ledger flips that. High transparency, Byzantine fault tolerance, strong cross-border properties at medium throughput. Hybrid designs keep a centric function is calibrated against published FBFT data. Everything runs from a fixed seed, and the code is shared as supplement material. The model couples 7 models: node growth, user growth, token dynamics, centralization index, and a throughput model. Sorry, it's X. We run 4 scenarios, each deliberate setting over 100 months horizon. Scenarios A is a tightly governed retail rollout using a Y style. Scenario B is gradual decentralization growing toward 600 nodes with sharding and segmentation switched on along the way. Scenario C pushed the user base past a million to test whether demand breaks consensus. And scenario D freezes scenario B and runs a coordinated attack. Let's look at what comes up. Here are scenarios A and B together. The red curves are the centralized baseline. The green curves are gradual decentralization. The headline is equity result. Under decentralization, the Gini coefficient of token holding falls from 0.89 to 0.20. 77% drops in concentration, and the centralization index rises from 0.40 to 0.91. But notice the throughput curve. It starts near 30, dips to about 27 around month 36. Then sharding lifts it to 54, and segmentation to about 76, and settling at 68. So decentralization is real, but it's costs roughly 3 years of flat throughput before scaling pays off. That valley is central finding. And the scenarios say asks a different question. If a CBDC suddenly gets popular, does user demand break consensus? We push the user base up and S curve to 1.32 million with sharding switched on midway. The answer is clear. Even as users explode and the network grows to about 300 nodes, throughput just tracks scenario B at the same node count, about 52 transactions a second. In other words, throughput follows node count, not user load. So if you expect rapid uptake, what you invest in this horizontal scaling, not consensus tuning. Scenario D is the attack result, and it's the one I'd most want you to remember. We sweep the share of malicious validators from 5 to 40% under a normal penalty and a double one. 3 findings here, as you can see. Below the Byzantine 1/3 threshold, doubling the penalty roughly halves the chance of a successful attack. But around 35%, there's sharp transition. Success rate near 0.85, and the penalties stop mattering. So economic deterrence is necessary, but not sufficient. About the threshold technical defenses, identity checks, state caps are non-substitutable. Next, a model you can't check isn't worth much. So here's the validation. We compare our throughput predictions against the published FBFT measurements on equal footing. For clusters up to 18 nodes, which is the size our design actually uses. The model agrees to within 20% on average. I want to honest about the last row. At 21 nodes, the error jumps. That's a regime we don't simulate it. The test bed is saturating there, reporting that boundary openly. It's part of doing the validation properly. So 3 implications. One is the throughput. Throughput value is real, but bounded plan for about a 3-year transition, not a permanent loss. 2. Economic deterrence has a hard ceiling at the Byzantine threshold, so technical defenses stay mandatory. 3. It's node count, not user count, that limits throughput, so capacity planning should follow nodes. And on AI, which everyone asks about, our position is that AI belongs at the monitoring layer. Fraud detection, adaptive tuning, not as the consensus layer. The tech model even gives a target, detect within 2 to 4 months. To wrap up, architecture is a quantifiable trade-off, not a slogan. Decentralization is achievable journey from 0.89 to 0.20, sorry. But it costs a 3-year throughput valley, and economic deterrence has a hard ceiling at the Byzantine threshold. Our contribution is deliberately modest, parameterized, evidence-backed vocabulary for discussing CBDC infrastructure, not a new architecture. The companion paper takes the same model into supply chain finance. That concludes my talk. Thank you very much. I'm happy to take any questions.
Thank you very much. Do you have any questions? Yes, please.
Thank you for your talk. Can you hear me?
No, okay.
Oh, okay. So my question is, you mentioned the tokenomics model AB 2023. So your results are based on that model, right?
Yes.
Yeah. Can you please say a few words, like explain the core ideas? What is this model about?
Okay, thank you for this question. Let me take a moment to think about it. It's a long time I take it.
Okay, so it's like very theoretical. It's difficult to explain in few words, right? That's how I understand.
Yes. Let's show it again and simulated it by experiment.
Okay, I have one more question. If you could please go to slide number 10.
Yes.
And the question is about scalability. So as we understand this slide, so it shows the users like 1.3 million users. But what happens in the real scenario when we have billions of users, like a normal in current Asian countries, we have billions of population. So will this model scale to billions? So what is the scalability for real large-scale population scenarios?
Thank you for raising this point. But actually, it's a little bit beyond the scope of this paper. But I'd be happy to discuss it further via email. So,
Okay, thank you.
Okay, thank you. By the way, are you going to be the next speaker for the other paper? Mr. Kumbutai, are you going to be the speaker? Okay, thank you very much for your presentation. And can we proceed to the next paper, your next paper?
Okay. Let's begin next one.
Okay. Once you're ready, please begin.
Mhm. Sorry. I forgot to show my photo. Okay, I'll start. This is second of two companion papers. The first one asked what ledger a CBDC should run on. This one turns outward. It asks what CBDC and blockchain deployed together due to a real domain, supply chain finance, and to the wider financial system. Sim simulation, read here through a policy lens. Let me start with why supply chain finance is the right place to look. CBDC is no longer hypothetical. Over 90% of central banks are working on it, and more than 130 jurisdictions run programs. So the interesting question shifts not whether CBDC arrives, but how its design choices interact with the domains that absorb it first. Supply chain finance is closest to that frontier. Its old frictions line up almost exactly with what blockchain and the CBDC offer together. The clean way to see it: blockchain carries the information flow, CBDC carries the value flow, and supply chain finance needs the both at once. The paper asks three questions: which supply chain pain point gave way to a joint blockchain and CBDC solution? What we learn from the very different national approaches, and at what uh, threshold paradigm goals become measurable rather than aspirational. Uh, the method has three strengths: a comparison of national cases, paradigm. Okay, sorry. This paradigm goals become measurable rather than aspirational. The method has three strengths, and again, a comparison of national cases or paradigms is built on it, and a simulation that ties goals to numbers. The discipline at the highlight and the simulations that ties goals to numbers. The discipline highlights every claim in the paradigm section is tested against a measured indicator later. Supply chain finance has three structural frictions: information asymmetry. A lender can't cheaply verify that a trade is real. Settlement delay. A letter of credit still take 5 to 10 days, and the SME credit constraint. Small suppliers lack collateral, so programs favor the big firms. The fix is two complementary moves. Blockchain handles the information flow, and this is now empirical, not just conceptual. Tang and Chen report blockchain to uh, resilience coefficient of 0.759 across 88 firms. And CBDC handles the value flow, a real-time programmable settlement. Here's what the joint employment looks like in practice. For reasonable financing blockchain proves authenticity, and CBDC releases funds in real time. The cycle drops from days to hours. For cross-border payments, a shared ledger plus synchronized settlement compresses days into seconds and cuts cost by 40 to 60%. For letters of credit, full documentation on chain plus conditional payment takes 10 days down to 1. These are real pilots, not thought experiments. Technological doesn't decide policy, so we compare three national patterns. Singapore is design-driven, a layered system with programmable money built in, and the regulator helps shape the protocol early. And the European Union is privacy first. The digital euro puts data protection ahead of programmability. And the last one, the United States, is markets driven. No retail CBDC commitment and innovation led by private platforms. These institutional choices uh, decide which deployment patterns are even viable in each place. For that comparison, we build a four-dimensional paradigm: intelligence, programmable value, plus data-driven insight, pre- uh, precision instead of broad strokes, and trustworthy, cryptographic trust that complement institution and letting a small firm prove its credit without exposing everything. Uh, Inclusive low-cost wallets that is unbanked, and cross-border multi-CBDC breeds that turn currency competition into infrastructure competition. Each of these four becomes a testable setting in the next section. A quick word on the model and on credit. As the AB 2023 model is the work of Katov and Butanov. We are implement it in Python as it again. And following their specification, we don't propose it, and the numbers are calibrated reproduction, not original measurements. It's same engine as companion paper. There, I read it as a technical validation, and here as policy. I wish it can answer your first question. And the logic is a chain. Each paradigm goes because becomes a policy archetype, and each archetype of parameters setting. Each setting a 100 miles trajectory. Here's the mapping itself. Scenario A is the retail archetype, is in Y style, tightly governed. Scenario B is the wholesale distributed archetypes, M bridge and Agora pattern, carrying the cross-border and trust goals. Scenario C is the high adoption supply chain case, where the user base scales past a million, and scenario D freezes B and tags it. For the trust goal, the mapping isn't arbitrary. Each archetype picks the settings its paradigm goes implies. Scenario A and B let a policymaker sees retail versus wholesale choice as a measurable trade-off. The encouraging result, a wholesale distributed CBDC reaches a Gini around 0.20 within the horizon, comparable to mature consortium chains. The sobering result, the centralization performance trade-off cost about 3 years of flat throughput when scaling lags behind nodes growth. Throughput dips to 27 around month 36. Then sharding and segmentation recover it to 68. The point for policy, this valley is real, bounded, and plannable. Scenario C matters most for this audience because supply chain platforms success exactly when adoption explodes. We scale the user base to 1.32 million as firms and logistics providers come on board. Does that demand break consensus? It doesn't. Throughput just tracks scenario B at the same node count, about 52 transactions a second. Throughput follows node count, not user load. So the policy reading is concrete. The binding constraint is horizontal scaling capacity, not the consensus layer. Provision for it upfront. Scenario D gives governance economics behind trust, below the Byzantine one-third threshold, doubling the penalty roughly halves attack risk, about 35% at saturates, and economic deterrence fails, so technical defenses become non-substitutable, and the model gives a monitoring budget, detect within 2 to 4 months. On credibility, the throughput model agrees with the published measurements to within 12% for the cluster sites we use. The full validation table is in the companion paper. So what does this mean for someone designing a CBDC and supply chain integration? 3 things here. First, choose a trade-off knowingly. Retail versus wholesale is a measurable choice, and the value only resolves if you commit to scaling early. And second, govern in layers. Economic deterrence below the threshold, technical defense above it, and AI monitoring on 2 to 4 months budget. And third, scale horizontally and early. High adoption stresses capacity, not consensus. None of this is a slogan. Each falls out of a measured trajectory. To wrap up, blockchain and CBDC resolve the core frictions of supply chain finance because one carries information and the other carries value. National paths differ by design.
Io sto ascoltando gli altri colleghi.
Sorry?
Sì.
Yeah, I'm assuming. The 4-dimensional paradigm is parameterized, not just asserted. Each dimension ties to a measured indicator, and the paradigm goals become attainable at a specific threshold. A 3-year valley, the Byzantine selling node count constraint, and the companion paper develop the technical side. That concludes my conclude my talk. Thank you very much. I'm glad to take question.
Thank you very much for your presentation. Okay, we're open for questions, comments. Okay, please.
Oh, hello, thank you for your presentation. Could you please show the slide number 5?
Okay.
So
Sure.
while you're doing it, the question is, at the bottom you have examples of the systems, and especially
This one?
Yeah, right. So at the bottom of the slide, you have the examples, right? So the question is, are those examples applied to real world, and do you know the scaling of them? Maybe right now they're like being piloted, and we have some results which is applied to real world scenarios.
It's a good question. I really want to use it in the real world, but it just need time to use it, test and correct go. When we get correct data, then we'll get better. We can design the best experiment to show the can I say shows the.
So did you use these examples as a baseline for your research?
Yes, it's baseline. We continue to use it data and this paper to get the more result. Yes.
Okay, thank you.
Thank you. We have other questions? Okay. Well, I guess thank you very much, Hu, for your presentation, and then we're going to proceed with the next. Okay, Michael. Michael.
Yeah.
Yes. Your presentation is 15 minutes, and another 5 minutes for questions and answer.
Okay. Everything
Okay.
is okay? Yeah.
Okay. Not. If you're ready, please start.
Yes, I'm ready. Okay. Hello, everyone. Today I will talk about a modernized version of basic Paxos consensus algorithm, which I call Orchestra Paxos. My name is Michael, and I'm a postgraduate student of St. Petersburg State University. I'm a student of Vladimir. He's an associate professor. Let's start with the agenda. First, I will briefly motivate the problem and remind you of a quorum-based replication. Then I will go through the Paxos mechanism that matter for this talk. And after that, I will focus on the limitations that motivate this work, explain the Orchestra Paxos approach, and exactly show the main experimental results. So let's start with the motivation. In water systems, we rarely have one server responsible for everything. We usually have thousands or a million instances, many replicas, and many possible failure points as a result of a high number of instances. For example, you can see on the slide inventory. Two clients try to buy the same last item at the same time, And if two replicas process these requests independently, both may accept their purchase, and the system becomes inconsistent. And this is a big problem. That's why consensus algorithm exist of prevent this class of problem. They let a group of nodes agree on one value or one operation, even when messages are delayed or some nodes are unavailable. This matters not only for databases, but also for brokers, coordination services, and storage systems. Many systems we use every day rely on some form of consensus under the hood. Let's move on to data replication task. And the theoretical background is a FLP theorem. And the result of this theorem in a fully asynchronous system, even if one process can fail, deterministic consensus with guaranteed termination is impossible. In practice, it means that if we can solve one of these bullet points on the slide, we can reach a consensus. And it means that algorithms have to work around the impossibility by using assumptions, timeouts, randomized behavior, or failure detectors. So let's move on the quorum. Quorum is a main point of consensus algorithm. Basically, simple majority quorum briefly is more than half of the participants in a system that agree with some decision. For this talk, the important idea is simple. Once a majority has accepted a value, a later majority must overlap with it and can learn about the accepted value. Let me quickly recap the PAX's roles. So a proposer suggests a value to acceptors. Acceptors vote on proposals. Then they broadcast this value to learners. Learners upload the result once the value has been accepted by enough acceptors. And in real systems, one physical node may play more than one role, but separating the roles makes the protocol easier to reason about. So Paxos has two phases, and in phase one, a proposer sends a prepare request with a round number and its identifier. Acceptors respond with a promise they will not accept proposal for all the rounds. The proposer needs a quorum of such promises. Then we move on phase two. In phase two, the proposer sends the actual value to all of the acceptors. And if the acceptors hasn't promised a high round, it accepts the value and broadcasts this value to all of the learners. And then they send an acknowledgement back to proposer. And when the proposer receives a quorum of acknowledgements, the value is considered chosen. The important part is that the quorum intersection keeps the chosen value stable across later rounds. Let me talk about my motivation of the modernized version of the basic PAXes. First, I would like to implement something new that will based on basic PAXes, also with high performance and fault tolerance, and solve a few limitations of basic PAXes. And let's move on for this limitation. The first limitation is that basic PAXes is a single decree. It chooses one value. But we know that the real systems need a sequence of decisions. That's why in production sphere use the consensus algorithm that based on the PAXes, such as multi-PAXes, that solve this by electing a stable leader and then reusing the second phase for many values, as you can see on the slide, and which reduces the number of messages also. The second limitation is competition. If two proposers repeatedly overtake each other with a high round numbers, the system may spend a lot of time in prepare and retire cycles. Backoff and randomized delays exactly can help us, but the problem still affects latency under unstable conditions. And the last third limitation is quorum failure. If a system has, for example, 3 acceptors and 2 of them are unavailable, classic majority quorum cannot be reached. The protocol remains safe, but progress stops. Okay, and let's move on the concept of orchestra access. Orchestra access keeps the basic access structure. It also have 2 phases, but it changes how the active acceptor set is formed. In phase 1, the proposer sends prepare messages and starts a timer. Instead of waiting for a fixed majority of all acceptors, it collects the acceptors that respond before the timer expires. This responding subset becomes the active acceptor set for that round. In a phase 2, then is executed only over the active subset. Inside this subset, we still use the standard majority quorum rule, and also proposer waits for quorum replies of confirmation until the timer is passes. So the algorithm doesn't simply accept one arbitrary responses. It chooses a value through a majority of the currently active set. The intuition is that the system should adopt to temporary failures and delays. If some acceptors are too slow or unavailable, they are not included in the current round. In the simplified example, the protocol can continue even if all but one acceptor are unavailable, because the active set may be reduced to the node that is actually responding. This is the central idea of orchestra access. And more information about orchestra access. Consensus guarantee based on standard access in phase 2. We use a simple majority quorum, and in orchestra access, we can reach a consensus even if n-1 acceptor nodes fail, where n is the number of all acceptors. I implemented orchestra access in Go language. The transparent LoRa is TCP/IP, and I also implemented a transparent emulator. The emulator lets me control bandwidth, round trip time, and message loss probability. In the experiments, I used 1.25 megabytes per second of bandwidth, 20 milliseconds round trip time, and write message loss from 0 to 60%. The comparison baseline with multiplexes, I used 3 metrics: average round time, total completion time for all rounds, and the number of rounds required to accept all proposed values. And let's move on to the result of comparison. The result is mixed but informative. When the message loss probability is low, multiplexes is clearly better, about 3 times on average across the metrics. This is expected because multiplexes is efficient when the leader is stable and the network is healthy. But when the message loss probability is high, orchestra access performs much better, about 12 times better on average in the tested cases. The reason is that the active acceptor set can adapt to the nodes that are actually reachable during the round. On this slide, you can see detailed experimental results in tables. When in the experiments was 3 participants in each row, and also when it were 5 participants in each row. Let's move on limitation of orchestra